Hi, welcome back to the lecture series on major theory with course code MMTC 202. Today, in this lecture, we are going to discuss the main theorems of abstract major theory. The first theorem is the Lavish theorem. Okay. So let us state this Lavish theorem. It's a Levy theorem. Levy theorem. It states that assume that a sequence fn, assume that assume that a sequence fn, a sequence fn, a sequence fn of integrable functions, a sequence fn of integrable functions of integrable functions of integrable functions of integrable functions satisfies fn less or equal to fn plus 1. That means this sequence is monotonic increasing almost everywhere for each n, for all n, and limit of the integral of fn, and limit of integral of fn is finite, is finite. Then the theorem says that then there exists then then there exists there exists an integrable function f, an integrable function, an integrable function f such that this fn, the limit of fn is f, such that fn increases to f, fn increases to f, and almost everywhere, and this limit of the integral also, integral of fn also increases to the integral of f. That's the statement of this theorem. Given a sequence of integral functions, monotonic increasing sequence, and with the condition that limit of integral of fn is finite, then we can find a function f, which is very important. It's very, so this is not a simple theorem. This gives the existence of the limit. Actually, there exists an integral function f, such that this f is the limit of that sequence, and the limit of the integral of fn is equal to the integral of f. Proof. So since fn increased to f, since fn increased to f, so which implies that fn minus f, fn minus f1, it is increasing sequence, so fn minus f1 is greater or equal to 0, because it is an increasing sequence. So that means fn is always greater or equal to f1 for all n, for all n greater or equal to 1. So therefore we can assume that our sequence is non-negative. If it's non-negative sequence, then we can replace our sequence fn by fn minus 1. So there now therefore we can assume that, therefore we can assume that Fn is greater or equal to 0 almost everywhere. If not, then we replace Fn by Fn minus 1. Fn minus F1, sorry. Fn minus, we replace this F by Fn minus F1. Fn minus F1. Okay. Also, we assume that we assume that this Fn is monotonic increasing for each n. Also, we assume that and it's non-negative for each n. This is monotonic increasing for all n greater or equal to 1. In the statement, it's monotonic increasing almost everywhere, but we can assume that it's monotonic increasing for each x, for all n, and x belongs to x. Okay, this is how we can assume. Now let I be is equal to limit of the integral of fn, which is finite. Okay, let's denote this limit by I, which is a finite number. Now for each, and since fnx is monotonic increasing, fnx is monotonic increasing, so therefore the limit of fnx exists finite or infinite for all x belongs to x. For each x belongs to this limit exists whether finite or infinite. So let's denote this limit by let g of x be its limit, be limit of fn x. So then this g is it's the extended real valued function. Then g is a function from x to r star, where this r star is equal to, where r star is, it's the extended real number system. R star is equal to set of all real numbers union, it includes infinities as well. It's called extended real number system. Okay, so this g some values of g may be infinite, so that's why this g is a function from x to r star. But we will show that the set where it takes the values infinity is null set. So let's denote that set by E. Let E is the subset of x such that g of x is equal to infinity. Okay, so we show that this is null set. We show that mu star of E is equal to 0. So first we note that, first we verify that, this E is equal to the intersection I runs from 1 to infinity, then union n runs from 1 to infinity of the set x belongs to x such that fn x greater than I. Okay, we verify this is this set. So this will imply that is measurable because fn is a measurable function, fn is integrable, and it's measurable. So that means this set is measurable for each n and for each I. So which implies the union with over I and union over n, and the intersection over I is also measurable, because as we know that the collection of measurable sets is an sigma algebra. So let's prove this. Let x belongs to this intersection union. Okay, intersection I runs from 1 to infinity, union n runs from 1 to infinity, x belongs to x such that fn x greater than I. So this is true if and only if x belongs to the union n runs from 1 to infinity, x belongs to x, such that fn x greater than I for all I greater or equal to 1. So this implies this is true if and only if x belongs to some one of fn. So that means this means fn x is greater than I for all I greater or equal to 1, and for some n, and for some n. So this means the limit of fn must be infinite, because for some n it's greater than I for each n, so which is true if and only fkx is greater than I for all I greater or equal to 1, and k greater or equal to n. Because fn is greater than I, so that means fk must be greater than I for k greater or equal to n, because as this fn is monotonic increasing sequence. So which means that which is true if and only if the limit of fnx, and that's the definition of limit at infinity, is equal to infinity. So which is true if and only if x belongs to E, because this is because this implies this is true if and only if g of x is infinity, because limit of fnx is equal to gx. Okay, so thus E is measurable. Thus is E is measurable. Thus E is measurable. E is a measurable set. Now we show that its measure is 0. Now since fn is integrable, and fn of x is greater than 0, so it's non-negative integral function. Therefore, fn is an upper function. It's already done. Therefore, fn is an upper function. It's an upper function. So for this upper function, we must have a generating sequence. So let's take its generating sequence. So let phi and I be the generating sequence. For fi, be the generating sequence for fi. So then this is also non-negative function. Then 0 less or equal to phi and I, and it increases to fi because it's the generating sequence for fi, and this is true almost everywhere by definition. This limit is with respect to n. Okay, limit with respect to n. So it is a generating sequence. For each n, let's define psi n now. For each n greater or equal to 1, define psi n, which is equal to join phi and I runs from 1 to n. Then psi n is the sequence of psi n is the sequence of step function. Then psi n is a sequence of step functions, because the finite supremum of step functions is again a step function. Is a sequence of step functions. And then this sign is a sequence of step functions, and such that you can easily verify this, such that this sign it increases to g. What's g? G is the limit of fn. So which implies that limit of psi n is same as limit of fn, and this will give, you can easily verify this will give limit of integral of psi n is equal to limit of integral of fn, which is finite, so thus sign increases to g, and its limit of the integral is finite. So this means that this also give this also give psi n meet k times characteristic function of E increases to, this will increase to k times chi of E. So you can easily verify this. Suppose x, suppose first case, let's say first, suppose x belongs to E. If x belongs to E, then this will be psi. This is true for each k, for all k, okay? For all k, for each k, this holds, okay? So now you take the cases. What's the sign? The limit of sign is g. Okay, the limit of sign is g. And g is whenever x is in e, then g is infinity. Then this limit of sign is g, which is equal to infinity. It is infinity meet k, which is equal to k, and on this side, it's this is also k whenever x is in e. So therefore, limit of this and this one, they are same whenever x is in e. So whenever x is in e, limit of sign is g, which is equal to infinity, because x is in e. So infinity meet k is equal to k. That's the limit of this. And this one, this is also equal to k whenever x is in e. So that means the limit of this is equal to k times chi of e whenever x is in e. Now if x is not in e, if x is, then this will be 0, and this is a non-negative number because sign is non-negative. So what's the meet? Meet will be 0. So this limit will be 0, and on this side, if x is not in e, this is also 0. So thus again the limit is equal to this. So that means this limit of sign meet k times chi of e is equal to k times chi of e. And this is now this one, it's it is the characteristic function k times characteristic function. This will give k times mu star of e is equal to the limit of this, already done. So the one of the theorem, it is limit of the integral of psi meet chi of e, but this is less or equal to limit of integral of psi, as psi meet chi e is less or equal to psi. So this is finite. This one is already done. It's finite. So which implies k times mu star of e is finite for all k. For all k, this is true. And this will give mu star of e must be equal to 0. Mu star of e must be equal to 0, because any number, any multiple of this mu star of e is finite. So if k is approaching to infinity, if mu star of e is not 0, suppose it's some positive number, suppose it is equal to 1, then k is finite for each k. Which is not true. For each k, k is not finite. Then this limit, then if we apply the limit over k, suppose this k is a positive integer, if we apply the limit, so this will not be less than infinity. The limit is not less than infinity in that case. So this mu star of e cannot be equal to some positive number, otherwise this will not hold. Okay, because it's you cannot say it's finite here. Sorry, it's this is not. I cannot on finite is it's always finite. For each k it's finite, but it's equal to some fixed number I. Okay, which is finite. So for each k, mu star of, if suppose mu star of e is finite, then for each k cannot be equal to I. You can say, or less or equal to I. Here it's less or equal to. K cannot be less or equal to I for each k. So that's why this mu star of e must be equal to 0. Then in that case, 0 is less or equal to I, which is true. So that means therefore is a null set. Therefore is a null set. Now we define f. Now define f from x to r by f of x is equal to g of x. If x is not in e, that means some finite number. Whenever g is finite, we take fx equal to gx. But if x is in e, then g of x is in infinity. So I will take f of x equal to 0 if x is in e. If x is in e, then this then fn increases to f all, then because then this f is equal to g almost everywhere. So therefore fn increases to f almost everywhere. So this fn is a sequence of upper functions because it's non-negative and it increases to f. So which means f is also an upper function. That means f is an integral function. So which implies this is already done in our one of our theorem. That is if we have a sequence, if f is a function from x to r, and we have a sequence fn of upper functions such that fn increases to f, then this f is also an upper function, and limit of the integral of fn is equal to, this implies f is an upper function, is an upper function, is an upper function, and is integrable, and is integrable. And thus it is done in previous theorem actually, and thus and thus limit of integral of fn is equal to integral of f, which is equal to integral of limit of fn. So limit of integral of fn is equal to integral of limit of fn, and that limit is equal to f. This proves the Lavish theorem. Now we have that's analog for the sum. It follows from this theorem. That's the next theorem. That is analog for sum. Okay, series actually. Let fn be a sequence of non-negative integral functions. Let fn be the sequence of non-negative integral functions, non-negative integrable functions, non-negative integrable functions, such that the sum is such that the sum of the integral is finite, such that summation I runs from 1 to infinity, n runs from 1 to infinity, integral of fn is finite, then this summation n runs from 1 to infinity fn defines an integrable function, and one more thing, that's the integral of infinite series fn is equal to infinite series of the integral of sum is equal to sum of integrals. For finite sum, it's true, it's simple, it's already done, but it's true for also infinite if this happens. Okay, if it's non-negative sequence and this integral is finite. So we'll apply Lavish theorem here. For this, we have to construct a sequence, monotonic increasing sequence, satisfying the hypothesis conditions of the Lavish theorem. So let's define G, and let G and X is equal to summation I runs from 1 to n fi. Since fi is non-negative, so therefore Gn then Gn is a sequence, monotonic is a sequence of integrable functions, because it's a finite sum of integrable functions, is a sequence of integrable functions, and this Gn is monotonic increasing almost everywhere, because G1 is f1, G2 is f1 plus f2, and these fi's are there non-negative. You are adding non-negative numbers actually. It's monotonic increasing almost everywhere also. And one more thing is that if we calculate this limit of integral of Gn, which is equal to limit and approach to infinity, what's integral of Gn? Gn is equal to summation I runs from 1 to n fi, which is equal to limit and approach to infinity, this summation is here, summation I, because it's a finite sum fi, and this is equal to summation I runs from 1 to infinity integral of fi, or you can say this is summation and runs from 1 to infinity integral fn, which is finite. So this here it satisfies the conditions of the Lavish theorem. So thus there exists a function g, there exists an integral function g, from x to r, such that gn increases to g, and limit of integral of gn is equal to integral of limit of gn. So this means, but what's the limit of gn? Limit of gn is g, but limit of gn, and this means this limit of gn, which is equal to series and runs from 1 to infinity fn, is an integrable function, is an integrable function, because the limit of gn is integrable function, is an integrable function, and this limit and approach to infinity integral of gn. What's integral of gn? It is summation I runs from 1 to n of I, which is equal to limit integral of the limit of gn is summation and runs from 1 to infinity fn, and on this side this is equal to, you can see, you can expand this finite sum, you can move out, you can pull out this sum from this integral, and you can see this is here summation and runs from 1 to infinity integral of fn, which is equal to the integral summation and runs from 1 to infinity fn. So this proves the theorem completely. Okay, so our next theorem is the Fatou's lemma. Fatou's lemma. Fatou's lemma. So its statement is let fn be a sequence of integrable functions, be a sequence of be a sequence of integrable functions, with the condition that they are non-negative also, they are non-negative, and limit inferior of the integral is finite, and limit inferior of the integral of fn is finite. It's given. The limit inferior of fn defined as an integrable function. Then the conclusion is limit inferior of fn defines an integrable function. Defines an integrable function, and one more thing, and this integral of limit inferior of fn is less or equal to limit inferior of integral of fn. This is the Fatou's lemma. If fn is the sequence of integrable functions, it's non-negative almost everywhere, and limit inferior of integral of fn is finite. Then limit inferior of fn defined as an integrable function, and its integral. Integral of limit inferior of fn is less or equal to limit inferior of integral of fn. Proof of this theorem, again without loss of generality, we can assume that they are non-negative without loss of generality. This fnx is greater or equal to 0 for all x belongs to x. So we can remove those null sets actually. So this is true for each x and for each n. Now let's define gnx, which is equal to infimum of fi x. I greater or equal to n. So g1x is equal to infimum of fi, I greater or equal to 1. G2 is equal to infimum of fi, I greater or equal to 2. Then you can see this, because if n is increasing, then you are taking the infimum of the lower sets, actually smaller sets you are taking the infimum small. For n equal to 1, you are taking the infimum of f1, f2, so on and so forth, and for n equal to 2, you are taking the infimum of f2, f3, so on. So you can see this, gn is monotonic increasing, then gn is monotonic increasing, and it's also greater or equal to 0, because fi's are greater or equal to 0, and it's also less or equal to fn. So this gn, it's monotonic increasing. So I will then 0 less or equal to gnx, and gnx is less or equal to gn plus 1 of x, gn plus 1 of x, for all n greater or equal to 1 and x belongs to x. And also this gnx, because it is the infimum of fn plus 1, fn plus 2, and so on and so forth, so it's always less or equal to, because it's the infimum of the set fn plus 1, so it's less or equal to each member of the set. So one of the member is fn itself, it's less or equal to fnx for all n greater or equal to 1. gnx is less or equal to fn. So this it's also 0 here, okay, 0 lesser. Now you can see this gn, it's a measurable function, because it is the infimum of measurable functions, so it's a measurable function, and it lies between two integrable function, as fn is integrable, g is 0 is integrable. So this implies, this gives this gn is an integrable function, so it's a sequence of integrable functions. It's an integrable function. It's integrable function. It's an integrable function. Okay. Gn is integral function, and it's monotonic increasing. Now let's look at the limit, so that we can apply the Lavish theorem. Now we can talk about the limit of integral of Gn, because it's monotonic increasing. But Gn is less or equal to Fn. So this limit is same as the limit inferior, actually, of integral of Gn, because limit inferior of integral of Gn is same as the limit of Gn, because limit of Gn exists. Limit inferior and limit superior are same. But this limit superior of this Gn, you can see here, this Gn is less or equal to, it's less or equal to Fn, so its limit inferior is less or equal to limit inferior of Fn. So this is less or equal to limit inferior of integral of Fn. Okay, and this is finite. It is given in the statement. So Gn satisfies all the conditions of Lavish theorem. Gn satisfies all the conditions of Lavish theorem. Okay. So thus there exists an integral function, thus by Lavish theorem, there exists an integrable function g such that Gn increased, g an integral of Gn increases to integral of g. This is Lavish theorem. Now what's g actually? Now this g is equal to, now what's g? G is actually equal to the, it's equal to the limit of Gn. G is equal to the limit of Gn. Okay, G is equal to limit of Gn. G is equal to limit of Gn. That's equal to the supremum of Gn, because Gn is monotonic increasing. What's Gn? That's equal to supremum infimum of fi is I greater or equal to n, which is the definition of limit superior, that's equal to limit inferior, sorry, it's limit inferior of fn. So this g is equal to actually limit inferior of fn. The g is actually equal to limit inferior of fn almost everywhere. You can see it's true almost everywhere. So this g is integral function. So therefore this one therefore limit inferior of fn is an integrable function. Integrable is an integrable function. Okay, this is an integral function. Now next you see this now integral of limit inferior of fn, it's equal to the integral of g, and that's equal to integral of limit of gn, which is equal to, by Lavish Theorem, it's equal to limit of integral of gn, but this one it's less or equal to limit inferior of fn, because this is equal to limit inferior of integral of gn, but gn is less or equal to fn, so that means limit inferior of integral of gn is less or equal to limit inferior of integral of fn. So this proves the theorem completely. Integral of limit inferior of fn is less or equal to limit inferior of integral of fn. The next theorem, which is very important, which is called the Lebesgue dominated convergence theorem. Lebesgue dominated convergence theorem. Lebesgue dominated convergence theorem. Lebesgue dominated convergence theorem. Okay, so its statement is that given a sequence of measurable functions, integral function is dominated by some integrable function, the limit is also integrable function. So that's why it's called a dominated theorem. Let fn be a sequence of let fn be a sequence of integrable functions satisfying mod of fn less or equal to g almost everywhere for all n greater or equal to, where g is an integrable function, where g is an integrable function. So this sequence is dominated by some integrable function. If now if this fn, if fn limit of fn is equal to, it is not monotonic increasing, its limit is f, then the theorem states that this f is an integral function, then f is an integrable function, and this limit of integral of fn is equal to integral of limit of fn, which is equal to f. So integral of f is equal to limit of integral of fn, or you can say limit of integral of fn is equal to integral of limit of fn. Proof of this theorem. So this fn is less or equal to g, so its limit is also less or equal to g. Clearly, mod of f is less or equal to g, so which implies minus g less or equal to f less or equal to g. This f is also measurable because it's the limit of a sequence of integrable functions, and every integral function is measurable. So it's the limit of measurable functions actually. F is measurable and it lies between two integrable functions because g is integrable. It lies between two integrable functions. Any measurable function lying between two integrable functions is again an integral function. So therefore f is an integral function. Therefore f is an integrable function. So then f is an integrable function. This one part follows. Now we prove the second part of this theorem. Okay, this f is an integral function. Now you can see this sequence. Consider a sequence. This one g minus fn. Look at this sequence, and you see this sequence satisfies the hypothesis of Fatou's lemma. This sequence it satisfies the conditions of this Fatou's lemma. It's a sequence of integrable functions because g is integrable, fn is integrable, and you can see this limit inferior of integral of fn, g minus fn is finite because this g is greater or equal to fn. So this limit is finite actually. It satisfies the conditions of this. So you can see this. Then this g minus fn is a sequence of integrable functions. And let's check this limit inferior of this limit inferior of integral of g minus fn. So you can verify that g minus fn is actually less or equal to g. It's less or equal to limit inferior of integral of 2g. You can see that this can be easily verified. This is finite because because we had this minus g less or equal to fn less or equal to g. Now you want to find g minus fn actually. G minus fn. Now let's applying throughout minus sign. So let's applying minus throughout. So we can see this this will become plus and plus g. It's greater or equal to minus fn and sign will change, which is greater or equal to minus g. So that means minus g less or equal to minus fn and less or equal to g. So from this you can see this 0 less or equal to, let's adding by g minus fn. You want to calculate g minus fn actually. So from this you can see what's g minus fn. Let's add g throughout. You'll see it is 0 less or equal to g minus fn less or equal to 2g. Okay, so this g minus fn is less or equal to 2g actually. G minus fn is less or equal to 2g, and 2g it is integrable, it is finite. So that's why this is here finite. So let me erase this here. So you can note this here. Okay, this is therefore limit inferior of g minus fn is finite. Okay, this is finite. This limit is finite. So by Fatou's lemma, now we can apply the Fatou's lemma, and not only this, and this limit by Fatou's lemma, limit inferior of g minus fn defined as an integral function. It's equal to g minus limit superior of fn, but limit of fn exists, so limit superior is same as limit inferior. It's equal to g minus f. G minus f almost everywhere. This is an integral function. So this is an integral function. Okay. Now by Fatou's lemma, now you can see this integral of g. You can see this integral of g minus integral of f, which is equal to integral of g minus f. Both are integral functions, which is equal to the integral of limit inferior of g minus fn, and that's less or equal to that's less or equal to, this is less or equal to limit inferior by Fatou's lemma integral of g minus fn by Fatou's lemma. Okay, by Fatou's lemma. Now this one, this is equal to integral of g minus times it will be now, because it's integral of g minus integral of fn. Then you can apply the limit separate, limit inferior of integral of g minus then plus limit inferior of integral of minus fn. So this will be equal to minus times can it's because limit inferior of minus fn is equal to minus times limit superior of fn actually. So this is equal to minus times limit superior of integral of fn. So we can cancel out this g. So this will give minus times integral of f is less or equal to minus times limit superior of integral of fn. It's limit superior of minus times integral of fn, and this implies integral of f. It's integral of f here, not fn on this side. This is your integral of f. Okay, integral of f is now greater or equal to limit superior of integral of fn. So name it 1. Similarly, on similar lines, you can see that on similar lines, we can see that this integral of f is less or equal to limit inferior of integral of fn by applying the Fatou's lemma, by applying the Fatou's lemma on this sequence g plus fn. Okay, on this sequence you can apply the Fatou's lemma. You can see this. So from first and second, we get this integral of f is less or equal to limit inferior of integral of fn, which is less or equal to limit superior of integral of fn, and that's equal to less or equal to integral of f by first. Okay, now you can see the ends of these inequalities are same. Okay, this means limit inferior is equal to limit superior equal to the limit integral of f. So that means limit of integral of fn is equal to integral of f. So this proves this Lebesgue dominated convergence theorem. Okay, this is a proof of Lebesgue dominated convergence theorem. Now next we can suppose we have a measurable subset E of a set X. Then we can take this measure space, which is can take the measure space E as a set. We can take its collection of subs and S is a summing, and with major mu, where summing SE is equal to, it's a restricted actually, it's equal to E intersection A, where A belongs to S. This is called a restricted summing. Okay, and for any subset E of X, we can define this measure space. And therefore we have functions from this E to R now, where E is subset of this measure set. And therefore we can discuss integrability over E as well. And you can see this is equal to integral over X f into the characteristic function of E. This is a very simple. This you can easily done. And from this we have following theorem: for any measurable subset of X, integral over X of f is equal to integral over E of f plus integral over E complement of f. That's simple because this integral over x of f is equal to integral over x, means you can say f into characteristic function of x, which is equal to e union e complement, because characteristic function of x is equal to 1, and you can e and in complements are disjoint. This is equal to integral of f into characteristic function of e plus integral of f into characteristic function of e complement. E is measurable, E complement is also measurable, and this one this is equal to integral over E of F plus integral over E complement of F. If you want to more explanation, you can see the page number 173, where you can see these every. Okay, this is and you can also see this theorem. Actually, this is the theorem: integral over x is equal to integral over e plus integral over e complement. This is theorem number 22.13. Okay, this is theorem number 22.13. This one, you can see that theorem. And also we can discuss the integral, the infinite integral as well. But if the integral of the function is infinite, we cannot say function is integrable, but we can say its integral is infinity. Okay, so this we discuss here, so that we can end this section here. Okay, so let's discuss integral of x standard real values function. Now suppose this we have function phi, which has a standard representation as it's a simple function, and these they are also suppose phi is a positive function, it's also a simple function. Phi has this representation ai into characteristic function of ai into characteristic function of ai. Okay, then what's the integral of f? It's not a step function, it's a simple function. Measure of ai is maybe infinite as well. Then integral of phi is equal to summation I runs from 1 to infinity. I runs from 1 to n, sorry. I runs from 1 to n. It's a simple function. It's I runs from 1 to n here. I runs from 1 to n. ai into mu star of ai. So mu star of some sets may be infinite, or if it is finite, then it's a step function. But here it's not a step function; it's a simple function. It may be infinite. In case it is equal to infinity, then we say this the integral of this step function is equal to infinity. Okay, and integral of phi is equal to infinity if measure of some sets are infinite. Now, suppose f is a function from x to r star. It's a real, it's an extended real valued function now. It's a function from x to r star, and it's also a positive function. Okay, it's positive r plus extended real number system. And suppose there exists, so you can substitute functions phi n. So you can substitute simple functions phi n such that phi n increases to f. Phi n increases to f. Then this limit of integral of phi n will define the integral of f. This exists as an external real number system, and we can say this is equal to integral of f. This may be infinity. If it is infinity, then we say this f is not integrable, but we can say its integral is equal to infinity. Okay, because f is the external real, because here the value may be infinity in this case. In this case, it may be infinity. And again, the integral is independent of the choice of f as a standard representation. This integral of phi, is independent of this choice. This is already done. So if f is extended real valued function, then this integral of f, and suppose there is a sequence phi n of simple function such that phi n increases to f, then this limit of integral of phi n may be infinity or it may be finite, and would define integral of f is equal to limit of integral of phi in that case. And in that case, we call this we do not call this function is integrable in case it is infinity. In case it is finite, then it is integrable. But in case it is infinity, we do not call the function is integrable. But in this case, we say this integral of f may be infinite or it may be finite. Its value is maybe infinite or maybe finite. Okay. So if we take this as a definition, then every positive measurable function, every positive measurable function possess this property. Possess this property. Why? Because for any positive measurable function, we can find a sequence of simple function non-negative such that that sequence increases to f, and then we can define this integral like this. Okay. So we can define the integral of every positive measurable function. The integral may be infinite or finite. Okay. Again, this we can express every function as a difference of two positive functions. F is equal to f plus minus f minus. So I want to explain that we can define the integral of every measurable function actually, not only positive measurable function, but every measurable function, which is obviously extended real number system. So suppose f is any function, it's a measurable function. Suppose f is a measurable function, then f can be written as f plus minus f minus. Both f plus and f minus are non-negative functions. So we can define there is a we can define the integral of this, which may be extended real number system, or integral of this, which may be which is the extended real number system. So we can define f plus and integral f minus. So in case one of them is finite, then we can define integral of f plus minus integral of f minus. This is extended real number. Suppose this is infinity, this is finite, then this is infinity. Suppose this is finite and this is infinity, then this will be minus infinity. So this is our integral of f. So one of them must be finite, then we can define the integral of f as like this, integral of f plus minus integral of f minus. Both cannot be infinity, because in that case this is infinity minus infinity, which is an indeterminate form. So suppose f is a measurable function, then it has this representation f plus minus f minus. Both f plus and f minus are non-negative functions, as already discussed. If f is a measurable non-negative function, then we can define this integral as an extended real number, and this integral as an extended real number. Suppose one of them is finite, then we can define this integral. So in that case, we have defined the integral of every measurable functions, and Fatou's lemma is true for those in general for those integral functions. So prove Fatou's lemma for sequence of integrable functions. Okay, for sequence of measurable functions only. For sequence of measurable functions. Okay, for sequence of measurable functions, not integral functions. For sequence of non-negative measurable functions. For sequence of measurable functions. Okay, for sequence of measurable functions fn, but that sequence is this is non-negative. Okay, so prove a Fatou's lemma for this sequence. So in that sequence, it's a sequence of measurable function which is non-negative, so that the integral of fn may be infinite, and you have to prove the Fatou's lemma for this sequence also. So that completes this section of integrable functions. In the next section, we will see the Riemann integral as a Lebesgue integral. So that's the last section of this chapter. Then and also this completes the course MMTC 202 and MTH 601. Okay. So next lecture will be the next lecture will not be the last lecture. It will take 2 to 3 lectures at least. So, but that will be the end of this unit actually, end of this course MMTC 202 and MTH 601. Thank you.